Okay, so we are interested in solving this eigenvalue problem, right? It's an eigenvalue problem because you have S as a parameter, which is an eigenvalue, and you have homogeneous boundary conditions for F. Okay, so these are the homogeneous boundary conditions. S is the eigenvalue. All right, now you want to solve this differential equation. You might as well guess the solution because you have the function f, which is the eigenfunction, which is satisfying homogeneous boundary conditions at 0 and 1. So you might anticipate that f of y should be proportional to some c sine n pi y. Okay. Now n is of course an integer 1, 2, 3 and so on. Right. So if I substitute this back here, what I will get is s times c sine n pi y is f is c sine n pi y minus 1 over r times, if I take the second derivative, if I take the first derivative, I will get n pi times cosine. If I take the second derivative, then I will take another n pi times minus sine. So n squared pi squared with a minus, let me minus n squared pi squared sine n pi y. Okay, and I'm sorry about this particular change of sign here. It should be plus out here. So that sign mistake should be rectified. It should be plus out here. So it should be plus out here. So what you will find is that sine n pi y and c, or the product of c sine n pi y, will cancel right through, right? And this will go, leaving us with s. Now I'll put an index n because it's a function of this number n, the integer n. So you'll get 1 minus n squared pi squared by r. Note that r is the control parameter. It's like the Reynolds number, which is in your hand, that describes this model problem. All right. Now what you could do then is you could then ask the question, when is this going to become unstable? So remember, you had e to the st. So you need s to be positive. S is a real variable here. So if you have positive values of s, then you know that things are going to become unstable. All right. So when you do this, so you could plot s as a function of the parameter r. Okay, this is the growth rate or the eigenvalue Sn. Okay, so depending on n, you will get many curves. Let's take n is equal to 1, you'll get something like this. Okay, get n is equal to 2, you get something like this. You get n is equal to 3, you get something like this, and so on. So n equals 1, n equals 2, and n equals 3, and these will cross 0 at precisely pi squared, 4 pi squared, 9 pi squared. All you have to do is set this to 0, so you'll get 1 minus n squared pi 1 minus n squared pi squared by r is 0. Okay, that is the point where it crosses 0, right? So what is that value of r at which it crosses 0? So r will become simply n squared pi squared. Okay, for different values of n, you will get different values of this value of r at which the eigenvalue crosses 0. So this is unstable because it is growing exponentially when a real part of s is positive. Okay. So this is the outcome of linear stability analysis, and you will be able to figure out which modes become unstable and when they become unstable as a parameter is varied. Okay, and the subscript n denotes that the growth rate of different modes, that is different n, are different. Okay, as you can see from this qualitative sketch. Right now, so when Sn is less than 0, the perturbations decay. So for r less than n squared pi squared. Okay, and when Sn is 0, perturbations are neutrally stable. That's when r is equal to n squared pi squared, and Sn greater than 0 is unstable. That is when r is greater than n squared pi squared. Okay, right. So now if you ask the question, what is the lowest r? This is called the critical value of the parameter r, the critical r for which this model system becomes unstable. If you ask this question, then you will obviously say from this graph that it is n is equal to 1. It happens for n is equal to 1 and r is equal to, so RC becomes pi squared for this problem. Although there are higher modes, n is equal to 2, n is equal to 3, n is equal to 4 and so on, but this is the lowest r for which the system becomes unstable. So this is called the critical parameter. In fluid mechanics, we will call this the critical Reynolds number. Okay, this is called the critical parameter, and so for r less than Rc, all eigenvalues are stable. When r is just greater than Rc, just the n is equal to 1 mode is unstable, and all the other modes are stable. But when r continues to increase, then subsequent modes can become unstable. But of course, whether those are relevant or not becomes a matter of it's a matter of debate, because you know that when r is greater than Rc, then the system becomes unstable, so the perturbations grow exponentially in time, and soon enough nonlinearities can become important. So it is not possible to see whether these higher instabilities, the modes of higher modes with higher values of n, those becoming unstable at subsequently higher values of r, whether they have any bearing on the actual physical problem, because you know that soon enough nonlinearities will become important. Okay, so now the other thing we could also determine from linear stability analysis is the physical form of the most unstable mode, the eigenfunction. This is the eigenfunction. Okay, so this is given by f prime of yt, which is nothing but it is some constant which is an arbitrary constant, because you know that eigenfunctions are not determined exactly, they are only determined up to a constant, multiplicative constant. Sine phi squared y is the most unstable mode, one with n is equal to 1, right, and times exponential of 1 minus pi squared by r times t. Okay, this is the spatial and temporal dependence of the most unstable mode. If this model were to be representative of an experiment, then this is the spatial structure of the most unstable mode that you will see. Okay, now I want to do the same problem in a slightly different context. Now I want to ask the question, we had, remember, you had f prime, if you remember the steady state, we said that f bar times 1 minus f bar was 0. This gave rise to two possibilities. Okay, Now, this possibility was chosen before. We said that f is 0 at y is equal to 0 and y is equal to 1. Now, we have the other possibility, but this possibility is feasible only if f is 1 at y is equal to 0 and y is equal to 1. So, let us choose this possibility now. Now, let us linearize about, let us say the boundary conditions are such that f of 0 is 1 and f of 1 is 1, then this will indicate that the solution is f bar is 1. This is one of the solutions of the nonlinear steady solutions of the nonlinear equation. Now, if you linearize about f bar is equal to 1, what you will see is partial f prime by partial t is f prime, okay, minus you have f squared. The equation that we are considering is df dt is f minus f squared plus 1 by r partial squared f by partial y squared. Okay. So, f becomes f prime. This becomes f bar. Okay, let us just do this in detail. Okay, minus f prime the whole square plus 1 over r times d squared f bar by dy squared plus 1 over r d squared f prime, or rather partial squared. Okay. Now, f bar is 1. Okay. So, this is 1 plus f prime minus, if I expand this, I put f bar is 1 plus, okay, 2 f prime plus f prime squared plus 1 by r. Now, this will become 0 because f bar is 1, its derivative is 0, right. So, you will merely be left with okay. Now, if you look at these two terms, this one will get cancelled with this one and this is nonlinear. So, what you will be left with is partial f prime by partial t is f prime minus 2 f prime plus 1 by r. Okay. This is nothing but minus f prime plus 1 by r. This is partial f prime by partial t. Now, we will use the method of normal modes. What is the method of normal modes? You will say that f prime of y t is some f of y, which is eigenfunction in the spatial direction, times e to the s t, and if you substitute, you will get s f is minus f plus 1 by r times by dy squared, and then we will again guess, and remember that the boundary conditions for the perturbations f prime is 0, because the base state has already satisfied the boundary condition that f bar is 1 at y is equal to 0 and y is equal to 1. Therefore, f primes will be 0 at y is equal to 0 and 1. Therefore, the eigenfunction f will also be 0 sorry, it should be y is equal to 1. Okay. Now, Sf is equal to minus f plus 1 over r right. Now, we will again guess f of y is some sine n pi y and substitute this back here, then you will get Sn minus 1 minus n squared pi squared by r. Now, if you ask the question, what will happen to this system, this model system? This is always stable for positive r. If r is assumed to be a positive number, and of course n is 1, 2, 3, 4, okay, Of course, r is negative, then it's another matter. You can say that this negative of negative will become positive, and this can become unstable. But if r is greater than 0, if r is some physical parameter that's greater than 0 always, then this is always stable. Okay. Now, let us solve the same model problem, the steady state, the stability of the steady state f bar is 0, such that the boundary conditions are this, and you would like to solve f prime. After linearizing, we got this ordinary linear partial differential equation. Okay, f, the boundary conditions are this. Okay. Now, let us assume we will solve this using as an initial value problem. How will you do this? You will say that f prime of y t is nothing but summation n equals 0 to infinity some constants a n e to the s n t times. Okay, this is the expansion of this is the eigenfunction expansion, because you know that f prime is a function of y t. It has to satisfy 0 boundary conditions. So, the eigenfunctions are sin n pi y. The time dependence has to be exponential, and there will be some constants which will be fixed by the initial condition. So, if you substitute this back in here, then you will get summation n is 0 to infinity a n s n e to the s n t sin n pi y is summation. This is also the eigenfunction expansion method to solve PDEs. Okay. Summation n is equal to 0 to infinity a n, the first term will be a n e to the s n t sin n pi y minus 1 over r. Okay, there is a minus because if I take the derivative twice, I will get a minus. Summation n is equal to 0 to infinity a n e to the s n t n squared pi squared sin n pi y. Okay. Now, I can pull everything in one side and take the common term a n e to the s n t sin n pi y as common times s n minus 1 by r n squared pi squared is 0. Okay. Now, if you do this, then because the signs are orthogonal, okay, if I take so the summation of all of this is 0, that itself means that if I take the orthogonal the inner product of this expression with, let's say, sin m pi y, then you will get that this term has to be 0. Okay. If I take inner product with m pi y, then you will find that a m e to the s m t times s m minus 1 by r m squared pi squared has to be 0. Now, you cannot have a m's to be 0, you cannot have e to the s m to be to 0. So, you will have this to be 0. So, or s m or s n is given by 1 minus n squared pi squared by r. This is the same result we got from the method of normal modes. So, in terms of finding out the eigenvalues, it is the same. But the only advantage of the initial value problem is that you can substitute this back in the expression for the original expansion. This you can substitute what is Sn, which we have found now, and if you have the initial condition, okay, times. Now, if we know what is f prime of y at t equal to 0, it is some function of y, let us say g of y, then I can substitute 2 equal to 0 here, which will give me a n sine n pi y, and you can find what the constants a n are for a given g of y, for a given initial condition. So, that will fix the complete time evolution of this whole thing, but the fact remains that the growth rates or the eigenvalues are the same whether you do it via the normal mode approach or the initial value approach. The initial value approach will give the answer with respect to the time evolution with respect to a specific initial condition, whereas the normal mode approach will merely tell you that for what critical values of the parameter at which things are going to exponentially grow in time. So, in the absence of initial condition, the best possible thing that we could do in terms of asymptotic stability is the method of normal modes. Okay? And this is something that is very, very important, and you should keep this in mind as we go along. Okay? So, in the method of normal modes, we completely sort of go away from the hope of solving the perturbation evolution equations for a specified initial condition, because we do not know the specific form of the initial condition, and all we know is that any random initial condition will have all kinds of Fourier components or eigenfunctions. So, there is nothing special about a random disturbance which will have one of these coefficients, for example, to be 0. So, if the flow is unstable to any one mode, then any random initial condition will also become unstable. Okay? That is the philosophy behind the method of normal modes. So, I will stop here, and in the next module what we will do is to review some basics of boundary conditions at fluid-fluid interfaces before we go into analyzing some specific hydrodynamic instabilities. So, I will stop here in this module, and we will meet again in the next module.